This is UCM Part 4, and this one we're going to start looking at problem-solving techniques. So to begin with, we're going to look at the equations that we have and see if we can develop a couple that we haven't talked about yet. So to begin with, let's talk about acceleration. The only equation that I've given you so far is actually the F equals mv squared over r equation. So we're going to start with that. But we're going to look at that see if we can find an equation for acceleration starting from this one. So we're going to divide both sides by m. If we do the same things to both sides, we can keep doing whatever we want with an equation, right? So here we have f over m equals v squared over r. If you remember from last semester, we studied Newton's second law, which is the F equals ma equation. If I rearrange that for acceleration, that gives me net force over m, which is the same thing that I have on my equation above. So I can say net force over m equals a, therefore acceleration equals v squared over r. That is the equation for acceleration for an object that is undergoing uniform circular motion. You'll use this one a lot, so this is a one to put a star by. Anytime you want to find acceleration in this chapter, you're probably going to be using this equation. Here's one for speed. Now, speed, just like any other time, is just distance over time. So if we're talking about a circle, the distance around the circle is actually the circumference, which is 2 pi r. So the equation for speed is going to be 2 pi r over period. Notice that the t here must be period, not just any time. Sometimes in a problem, they will give you the time it takes to go around half a circle, or the time it takes to go around twice, or they'll do something silly like that. So you just need to make sure when you use this equation, it's specifically the period, the time to go around once. Notice here they use v. They use v for speed. It's kind of annoying because the velocity is constantly changing. Because the direction is changing, the speed stays the same. But the physics symbol for speed is sometimes written just as v. So this is the equation for speed. So whenever you see a problem and you identify it as a circular motion problem, here's a general strategy that you can look at. It's a little different than some things that we've done in the past. They're talking about forces, usually component forces, when you have circular motion problems. So anytime you see something with those component forces being tension, gravity, normal force, any of those component forces, you should draw a force diagram. It's always useful when you talk about circular motion to identify the forces that are going inward towards the center of the circle and forces that are pushing outward from the center of the circle. So that will help you define the signs on the component forces that you've put in your force diagram. Notice that the only forces that we care about here, as far as the circular motion ones, have to be in the plane of the circle, so along the radius. Occasionally we'll see some where you have forces that are perpendicular to the plane of the circle. Those are not used in the F equals mv squared over r equation. If we use the F in that equation, it has to be the net force, and that has to be along the plane of the circle. So that's important. And I'll show you where you're going to see some of that in an example coming up. So you'll write the equation for the net force. You generally do that in any mechanics problem where you're solving for net force. Normally it makes sense to make the inward force positive, the outward force negative. Honestly, you don't always have to do it that way, but you always have to choose whether the inward or the outward is positive or negative and be consistent with that. So just as a general problem-solving strategy, since you're just starting out, make the inward force positive, the outward force negative. That'll always work out for you. And when you add those forces together, the inward and the outward, that will always give you the net force. But if you don't have the signs correct on those component forces, it will mess it up. So be careful about signs when finding the net force. Once you've found the net force, you can usually then solve for any unknowns that you're looking for in the problem. That's a general problem-solving strategy. Depending on what you're given in a problem, you may have to tweak that to make it work out for you. That's the thing I actually like about physics problems, is that they're kind of like solving a puzzle. They're not always the same way, and that's kind of fun, I think, because you just kind of have to figure it out. But if you kind of come at it from a certain strategy, just like if you're, making a puzzle, a floor puzzle, or some picture puzzle that you're working on, you always start with the corners and then do all the sides. You have to have some way to approach it. That's what we're talking about here. So I'm going to start from a qualitative example, and then I'm going to make it quantitative. So starting by looking at the concepts here. So we've got a tennis ball attached to a string, and we're going to spin that vertically. So up and down is the way this tennis ball is going to go, and it's attached to a string. So that means we know that we have tension in this problem. So to start with, we're going to do a force diagram for the ball both at the top and the bottom of the swing. I'm not going to care about the sides of the swing for this particular problem. So at the top, I know that I've got a gravity force, and because I have a string, it's a fairly safe assumption that I'm going to have tension. Gravity, you know, is going to point down. The tension, when the ball is at the top, should also be pointing down. Now, here's a side note for you. The slower you spin that ball, the less tension force you're going to have. At the slowest speed that you can spin that ball and have it continue in circular motion, at that slowest speed, you could go to the point where you have no tension at all, and the only force on it at that point would be gravity. So that is an option, that you could only have gravitational force at this point. The faster you spin it, you're going to increase and increase and increase the tension. And you've probably had that experience if you've ever spun something attached to a string. The harder you spin it, the more tension you're going to have. So that's the top of the swing. So if we look at the bottom, we have the same two forces. We know that tension at the bottom is going to be up. Will gravity be up? Of course not. That would be silly. So we've got the tension up and the gravity down. Now the force of gravity is going to be the same in both situations because the mass of the ball is the same, and the force of gravity is only determined by mass times 9.8. So since that's not changing, we have the same gravitational force. The tension is what's going to be different here. I made the tension much greater on the bottom, and the reason I did that is because if we're going to be in uniform circular motion, the net force is going to be the same. So for the top, the Fg plus Ft is going to be equal to the net force. For the bottom, I have to have that same net force value where the tension is actually in the opposite direction as a gravitational force. And I'll talk more about the signs here as we get into it. So my part B, we're going to label the forces as inward to the circle or outward, and we talked about that in our problem-solving strategy. So for my top, both of these are going to be inward forces because they're pointing towards the center of the circle. For my bottom, I'm going to have in towards the center of the circle for the tension, but the gravity force on the bottom is actually going to be outward from the plane of the circle. The reason I bother talking about this is those are going to tell me something about the signs. So I know that for the top, those two forces, since they're both inward, have to be the same sign. And for the bottom, since I have an inward and then an outward force, those tell me those have to be opposite signs, and that's very important for finding the net force. So then I can write the equation for the net force, and they're actually both going to be the same, that the net force is equal to the tension plus the gravity. But I know mathematically they'll actually be a different value because I have a difference in direction. Part D. What is the reaction force to the force of the string pulling on the ball? When you see reaction force, that should give you a tip that they're asking you a Newton's third law question. Remember Newton's third law, you have to have two objects acting on each other. So if my action force would be the string pulling on the ball, my reaction force would be the ball pulling on the string. So that would be the opposite. And you'll see some questions like that, which is why I threw that in here. So let's finish this off on my last part for this question by making this quantitative. And I'll give you some more practice on quantitative ones. But since I already have an example set up here and we've talked about the net force equation, it makes sense. So in this case, I'm going to go ahead and give you the mass and the velocity of the ball and the radius. So the question is to find the tension at the top and bottom of the swing. So we already have our net force equation is tension plus gravity. We can find what the gravity force is. That's the mass times 9.8, and that will be the same regardless of the position of the ball. So now we can also find the net force. If we're moving at a constant speed, this will also be the same. So since they gave us that velocity and the mass and the radius, I can go ahead and find the net force. Now I have the net force, and I already have my Fg. So I'm going to find my tension force at the top and the bottom. My tension force will be different based on the position of the ball. So at the top, I've got net force, tension, and gravity, and I want to see what direction they're all in. At the top, they're all pointing down towards the center of the circle. That means all three of those things have the same sign. So when I put the numbers in, I made down negative just out of habit, and that gives my net force and gravity the same sign. So when I add over the gravity to the other side, I find my tension force there, or subtract the gravity over. So there's my tension force, negative because it's pointing down. So now I look at the bottom. I have the same numbers. The only thing that's different is the direction. So in this case, my net force and my tension are up while my gravity force is still down. So when I put the numbers in the equation, I put my net force as positive and my gravity force as negative. That's going to result in a different tension force. So I add over my 0.55 newtons there, and I get a tension force of 3.35 newtons. The sign comes out to be positive, which agrees with the idea that the tension force is up. So this is our first basic quantitative example. We'll see more. It's most important to make sure you understand the concepts of what's up, what's down, our problem-solving strategy, and we'll keep working on it from here.